Okay, hello everyone. Today we're going to go over the calculating the acid dissociation constant for a weak acid. So in this experiment last week, we titrated a weak acid using our strong base sodium hydroxide. So after generating the curves, you should have got a data point. I'm just going to use some random data I generated to illustrate the calculations, but let's get started. Okay, so I'm going to share my screen here. So I'm going to go to the whiteboard. Okay. You might see me pop out a little bit. I'm going to turn off my view here so it's not so you don't see my underneath my head and stuff, so it's not so weird. Okay, so for example, hold on here. Let's see here. Okay, so for example, once so you want to find the equivalence point. So so let's go over calculating our molarity. Okay, so you know what? I'm going to use my other default app because the whiteboard here is not very good. So let's just stop sharing this, and I'll go to my I'm just going to share my screen here. Okay, so I'm just going to go to my notes page. Okay. So in this case, we have so here's calculating, see much better, calculating molarity of our acetic acid solution. So we made our acetic acid solution, right? But we don't know exactly how much is in there. So we're going to just ballpark it right here. Ballpark it. What I mean by that, we're going to we determined the concentration, right? We made the solution. So that was kind of a ballpark estimate. But now with the titration, we can accurately determine how much is in there and confirm out to some more significant digits. So let's see here. So say you did your titration curves and you already calculated the equivalence point. So let's say the equivalence point, I don't know, it's around 12 mils. So equivalence point, let's just say equivalence point is around 12.15 mils of sodium hydroxide, okay? And we know our molarity for sodium hydroxide, let's just say it's 0.205 molar. So maybe you determined that in last week's experiment, or when we did the strong base titration. Now, if you don't know, you should have figured this value even if you did the graph. So for the sake of future experiments, just use the value you determined in last week's post lab for strong acid, strong base. Okay. So our equivalence point, we have 12.15 mils of sodium hydroxide, 0.205 molar. So the chemical equation is, the reaction is we have acetic acid, CH3, COOH, an aqueous solution, plus sodium hydroxide. And this will give us a solution of sodium acetate plus water. So you see right here, we have a 1-to-1 ratio between sodium hydroxide and acetic acid. So you see the equation is already balanced. So there's a 1-to-1 ratio between acetic acid, and sodium hydroxide. So see, everything's balanced. So we're all fine and dandy here. So that means that at my equivalence point, so 1 mole CH3 COOH equals 1 mole, or sorry, let's just say moles. Moles of acid equals moles of my base here, equals mole of sodium hydroxide at equivalence point. So at my equivalence point, I've added enough base to react with all the acid. So the mole of acid I had means that there's no more acid present, because all my base I added has reacted with it. So we can say at that point, moles of acetic acid equals moles of sodium hydroxide at that point. So since it's a 1-to-1 ratio, let's calculate the moles here. So we have 0.205 mole per liter for our molarity of sodium hydroxide. Okay. And then when we multiply that by the volume here, we have to convert it to liters. So we're going to do milliliters. And to convert to liters, we're going to multiply by a factor of 1 liter is equal to 1,000 milliliters. So our units will cancel here. Okay. And if we do that calculation now, we should get a value of, so we have 0.205 times 12.15 divided by 1,000, and we get a value of 2.49 times 10 to the negative third. And this makes sense, right? Because our value for acetic acid, the way we made it, it was pretty dilute. So that's moles of sodium hydroxide. And now, since we know that moles of sodium hydroxide equals moles of acetic acid at the equivalence point is a 1-to-1 ratio, this means we have 2.49 times 10 to the negative third mole acetic acid. Well, let's just write that down to illustrate. We know from the mole ratio of our equation, 1 mole of sodium hydroxide gives us 1 mole of acetic acid. So therefore, we have also 2.49 times 10 to the negative third mole CH3 COOH. So let me just move that aside here. Okay. All right. So then we have, now we have the moles of our acetic acid. Now we just have to divide by the volume. So our sample was, so now to find molarity equals moles over volume of our sample. So we're going to say 2.49 times 10 to the negative third mole of acetic acid. And we know for our sample that we did each titration, let's go back to the procedures here. We did a titration of 30 mils. So 30 milliliters here, or we can say 30 mils or 0.030 liters. So we're going to put 3 sig figs because we have 4 sig figs because we measure out accurately 4 sig figs of our volume. So then if we do that calculation now, we should get 0.00249 divided by 0.03 And we get a roughly 0.083 molar. Okay, so now obviously these values are not, your value will probably be closer to 0.05 molar because that's the solution you made. So it should be really close. If you did it very precisely, you were very patient. Mine here uses usually made up data, so it won't be as accurate. So don't get flustered if you don't have 0.083 molar of acetic acid. So don't worry, this is just a calculation to illustrate a point. Okay, so that's CH3 COOH. Okay, so now we have determined our concentration of acetic acid. Now I'm going to go to the next part of the calculations. We're going to do, so after you generate your curves, your graphs, you're going to go through these calculations. It should make it pretty much more simple, simple to do these calculations after you did the graphs. Okay, so that's part A. So this is calculating molarity of acetic acid solution. So let's label that part A. Now let's go to part B. B is determining Ka of acetic acid Okay. So there's three parts. Determine Ka of acetic acid prior to titration. So let's do that. Okay. Okay, so all right, so let's see here. Let's take a sec to kind of read over what we should do. So okay. So what you want to do here is what we call an ice table. So ice tables will become very important when we talk about equilibrium. When you talked about equilibrium, so you may have seen this already. So what you do is you set up a table here, and you're going to label here. Here's your I or initial change for C, and then equilibrium is the equilibrium concentration. So I means initial change, and this means at equilibrium. Okay, so first we have our generic equation HA, but in this case it's going to be CH3 COOH is going to react with the sodium hydroxide or donate. So we're not actually, we're actually just talking about the Ka before titration. So if acetic acid was in water, how acidic would it be? So we're going to react with water. So it'll be in solution plus water. And that will give us a situation where we have an equilibrium state, and we're going to have the conjugate base CH3 COO minus, so that's our conjugate base, plus H3O plus, where water acts as a Bronsted base. Like so. Okay. So what would our change be? So we know at our initial concentration was 0.05 molar. Okay. And then initially we had 0 of the conjugate base and 0 of the conjugate acid as well. So the conjugate acid was water, the conjugate base was acetic acid. Those were 0 at initially. So our change is, according to some dissociation constant, acetic acid will lose some of its acid molecules and convert it to its conjugate base. So what we say is the change is represented by 0.05 minus some constant x or some variable x. And the amount that was lost to the acid is going to be formed, that it's going to form the conjugate base. So and on the other side, we say plus x and plus x for the acid as well. Then our equilibrium concentration would be our original molarity, 0.05 molar minus x. And then at equilibrium, at our A minus or our conjugate base, acetate will be x, and our H2O plus will be x as well. Okay. So how do we set up the Ka? Well, the Ka, remember, is the products over reactants. So for acetic acid, it'll be H3O plus multiplied by CH3CCOO minus, so 0, so the conjugate base. So this was before the titration even began. So at 0.0, you could have recorded a pH. Okay, so let's calculate a value now for our Ka here. So we know that if we can find the pH, that value that dissociated, or that value that represents the concentration of H plus or H3O plus that dissociated, that should also equal the concentration for acetate, because they're in a 1-to-1 ratio. So we figure out that pH, that'll be good. So maybe the pH was at let's see here, maybe 3.3. All right, so let's say the pH was initially at 3.35 or 3.25. All right, at 0 mils sodium hydroxide added. So at the start, we had a pH of 3.25. Now to calculate pH, the concentration, remember, we raise the pH to the negative power, negative 3.25, like so. And we should get the concentration of H plus. So let's do that right now. 3.25 negative, raise it to the 10th power of X. And we see our concentration is 5. Let's get 2 sig figs, 5.6 times 10 to the negative 4th power. 1, 2, 3, 4th power molar, and this is equal to my H3O plus. Okay. Okay, so that's our concentration of acid. So that will also equal our concentration of acetate, because that's how much acid dissociated. And we know that from our solution we made, the concentration of acetic acid is going to be around 0.05 molar. So that's before the titration. So we know the concentration there. Okay. So if we plug everything in here, we get 5.6 times 10 to the negative 4 squared over 0.05. Okay, and if we solve for that, we will get we will get our value here. So let's do 0.0000056 squared divided by 0.05, and we get a pKa of about 6.3. 1, 2, 3, 4, 5, 6. 6.3 times 10 to the negative 6 molar. Or 10 to the negative 6. So that's our Ka expression. So now if we look up the pKa of, sorry, not the pKa, but the Ka of acetic acid. So let's just Google it right here. Acetic acid Ka expression or Ka value. We should be able to get a table. You could just look at any table on the internet. Pretty much, it'll tell you what it should be. If I can find it. Okay, so if we just look at acetic acid here, it says its pKa is around 4.756. So if we just take the inverse of that, we take the negative, the antilog of that, we should be able to find the Ka. So 4.756 negative, take the inverse log, and we get, it's about 1, 2, 3, 4, 5, 1.8. So the actual Ka is, so we're kind of off. It's actually 1.8 times 10 to the negative 5. So we're kind of off by a factor of 10, but that's okay. This is a crude calculation of our Ka value. So we're now going to calculate it more accurately using our titration data. Okay. Okay, so your data will probably be much more accurate. These are numbers I am making up. Okay, so for the rest of the calculations, you're going to determine the Ka prior to titration, calculate the standard deviation, and you're going to do this for all 3 trials. So do it prior to titration. Now let's do it at the midpoint. Okay. Okay, so let's move down here. So now this is going to be, oops, did I stop sharing? My apologies here. Let's go back to Zoom. Okay, so let's go back here. So now we're going to calculate, determine. So determine Ka of acetic acid at the midpoint. So in this case, the midpoint is where, so the midpoint is where 1/2 of the original acid, 1/2 of the acid or the original acid. Okay, the original acid remains in solution, and the other 1/2 is the conjugate base. So in this case, our conjugate base is acetate, CH3COO minus. Okay, so at this point we get an equation where okay, so I'm not sure how we learned this equation, but the equation you probably should use, there's two ways we can do this. So at the midpoint, we know that 1/2 of the original acid remains in solution and the other 1/2 is a conjugate base. So you may have heard of this equation, pH equals the pKa plus the log of my base. So my conjugate base, COO minus, over my acid. So this is called the Henderson-Hasselbalch equation. And we use this equation to calculate the pH of buffers when we know the ratio of my acid and conjugate base. But since they're equal now, they cancel out. So this turns into 1. So this equation will turn into pKa plus the log of 1, because if your acid equals your base, they're going to be the same number. And when you divide a number by itself, it's 1. So this will go to 0. And at the midpoint, my pH should equal my pKa of acetic acid. So in this case, my pH should be about 4. Let's go up right here. We said right here, if you look at the pKa, it's about 4.76. So 4.76 should be my pH at the midpoint. But you'll be able to calculate that using your data. I'll explain how. Okay, so at this stage, you should use, so remember at the midpoint, so your midpoint should be 1/2 your equivalence point. So we're going to calculate and see how close our value is to 4.76. So your midpoint should be 1/2 your equivalence point. So it should be 1/2 of how much base you add. So this should be 1/2 of the volume of sodium hydroxide it takes to reach the equivalence point. So you want to take your value determined from the graph and divide it by 2. So let's say mine is around 5.5 mils or 5.45 mils. Okay, so we will determine the pH of the solution at the midpoint. So let's say at 5.45 mils is of sodium hydroxide is my midpoint. Okay. So you will record the pH. Maybe it's like 8. Well, it wouldn't be 8 actually. It'll probably be something below 6 still. So maybe it's like, I don't know, your pH is like 4.5. Okay. So using the midpoint pH, we say maybe the pH is about 4.55. Okay. So now we calculate again using the same equation. So we so at the midpoint, our concentration of acid, remember, it's going to be we're now going to calculate it this way. So remember our expression Ka equals H3O plus. So Ka equals H3O plus over acetate divided by our concentration of Okay, so using our concentration of acetic acid on the bottom here. Okay. Oh, sorry. I actually made a little bit of a mistake over here. So, my apologies. Let's go back to this. So you see here, we should have said minus x. So this should have been minus 5.6 times 10 to the negative 4. So since we determined that 5.6 times 10 to the negative 4, that is our concentration for x for H3O plus and acetic acetate, we need to subtract that in our denominator there. So let's go back and calculate that. My apologies. So we get 0.05 minus 0.0056. And you notice that's going to be really small still. And this turns out to be, so this equals 0.04944. So not a big difference, but still it will affect our calculations. So let's recalculate that now. So we have 5.6 e to the negative 4. Okay, that will give us square it divided by 0.04944. So now our answer should be, so it's not at all very different. So it's still 6.3 times 10 to the negative 6. So but to be completely accurate, we should put that number. Okay, so now let's go over here. So now we use the same kind of table here, the ice table. So the ice table we had before, we do initial change equilibrium. So here's our acid, CH3, COOH. But in this time, we have to, okay, I think I got it. We actually don't need this data table. So we know at the equivalence point that 1/2 of it is in the acid form and 1/2 of it is in the basic form. So that means our simplified equation is H3O plus is going to equal CH3COO minus, which equals the amount of acid that's still present in the equivalence point, at the midpoint, sorry. So if we calculate the pH, we'll get all those values. So let's do 10 to the negative 4.55. That will give us 4.55 anti-log. We get 2.8 times 10 to the negative 5th. Okay. So now if we plug that into our equation there, we should get Ka equals 2.8 times 10 to the negative 5th squared, because they're the same for both acid, the H3O plus, and the acetate ion, divided by 2.8 times 10 to the negative 5th here. So we get a value of 2.8 times 10 to the negative 5th. Okay, so that's our Ka. Now, if we compare that to the one at the equivalence point, that's pretty close, only off by like it's in the same range, so it's still pretty much the same here. But see here, we don't need to use the our ice table, because we know at the pH at the midpoint, the acid concentration is going to equal to the amount of conjugate base there, and the amount of H3O plus that was reduced is equal to the amount of base conjugate base produced. So we can backtrack and say all those concentrations should be the same, and you should arrive at an answer that is close to the Ka or pKa of acetic acid, which is the pKa is 4.55. Sorry, not 4.5, not 4.55, 4.76 right here. So if we were to calculate this pKa now, we would do 2.8 e to the 5 negative log and take the negative value. So that gives us a pH of around 4.55. So we just went backwards. So it'll give us a pH of 4.55. And that's pretty close to the pKa of acetic acid, which is 4.76. So that's a pretty good approximation. So your value should vary, but they should approach close to the 4.76 mark. If it doesn't, please go back through these calculations and try it again. But we know at the midpoint, if H3O plus is equal to my amount of acetic acid, the conjugate base that was produced, we know that at the midpoint, 1/2 of the original acid remains in solution, and the other 1/2 is the conjugate base. So in that, at the midpoint, we say that the midpoint concentration of CH3COOH equals the concentration of CH3COO minus, or the conjugate base. And we can use the Henderson Hasselbalch relationship to determine the Ka there. So getting pretty close. All right, so let's do it after the titration. Or at the now for the last step, we're going to determine the Ka at the equivalence point. Okay, so let's do that right now. So the last part, this is part B here. No, here's part C. So part C, determining Ka at the endpoint, or at the equivalence point. Ka of acetic acid at the equivalence point. Okay. All right, so let's just read about it right here. Equation. Let's see here. All right. Okay, so okay. So for the last part of the data analysis here, we had to do a little more calculation. So at the equivalence point, we know that the amount of base added, or sorry, we know that the moles of base equals moles of acid. So in our equation, we added enough. So for example, in our ice table here, we know initially we started with 0.05 moles. So 0.05 molar, right? So at the equivalence point, we added enough hydroxide where we added enough moles to get to the equivalence point. So in this case, let's just say we've added enough for 0.05 molar. So when that reacts, the change is minus 0.05. And here's going to be 0.05. But what we add at the equivalence point is going to produce plus 0.05 and plus 0.05 of water. But we don't care about water because it's the solvent. So our change here, we should have 0 acid and 0 strong base. And at the equivalence point at the end, we should only have 0.05 molar of water and of acetate. So now my expression is going to be a little bit different because what's controlling the pH is the conjugate base's reaction with water. So the reaction now at the equivalence point is, so at equivalence point, my base, acetate, is going to reestablish an equilibrium with water to form the acid. So we're going to get CH3COOH aqueous plus hydroxide ion. Okay, so let's move a few things over a bit. Oops. Okay. All right. So now we have a situation where we have this base expression, the conjugate base of acetic acid, acetate, reacting with water to reform the acid plus hydroxide ion. So this is known as a Kb expression because it's using the base. So we can write Kb as my acid, HA, CH3, COOH, the hydroxide ion, OH minus, and then we can use the expression here at the bottom for my concentration of OO minus. Okay, so at the equivalence point, we know that the concentration of acetic acid should now be roughly equivalent to my acetate because all they got reacted in solution. So my CH3 concentration, so at start of titration, now that should equal my concentration of my conjugate base. In this case, CH3 COO minus, that should equal now to 0.05 molar. Okay. Okay. Okay, so if that reacted, that means, so we use that initial concentration, right? So our initial concentration, we're going to figure out the concentration of the acid and the hydroxide that forms. Okay. So now we need to solve for Kb. We know our acetate ion, that should be 0.05 molar. Now we need to find out the how much dissociated to form the hydroxide ion and the acetic acid. The acetic acid that reforms from this equation. We need to look at the pH. So the pH will tell us. So the pH. So say your pH is like, I don't know, maybe like 11. So let's say your pH is 11.1. 11.15. Okay. So we know that pH plus POH equals 14, right? So pH plus POH equals 14. But to find the concentration of hydroxide ion, we need to know pOH. So pOH in this case will be 14 minus 11.5, and that's about 2.5, I believe. Let's double check here. Okay, so yes, about 2.5. So if I take the antilog of negative 2.5, I will get my OH concentration. All right, so take the negative antilog of that, we get 3.2. So let's make this 50, just so we have the same number, sig figs. 3.2 times 10 to the negative third, 10 to the negative third molar of hydroxide ion. So if we know that, that's also equal to the amount of acid that formed based on our ice table, right? So let's spread that ice table here. So we know for our ice table, for our next ice table, we have initial change, equilibrium. We have acetate plus water going to acetic acid plus hydroxide ion. So in this case, we have initially we had 0.05 molar minus, and that will react with water, right? So initially 0.05 molar, and we look here, that's exactly what we have here. Then the change is it's going to be minus X. So at equilibrium 0.05 minus X, and then it's going to produce a value for our acid plus X and plus X for hydroxide ion. So if we know that X, so this will equal our X here. We know X, we can figure out the equilibrium concentration for acetate. So in this case, our equilibrium will be, so it'll be 0.05 minus 3.2 times 10 to the negative third. And this will be 3.2 times 10 to the negative third. Oops, let's put this on the bottom here. X. 3.2 times 10 to the negative third and 3.2 times 10 to the negative third. So now we have all these values. We can plug them into our Kb expression. So let's first solve for the amount of acetate that remains, minus 3.2 e to the third negative, and we get 0.0, let's say 468. Keep all the sig figs. Okay, so now we can plug this to our Kb expression up there. So Kb equals, let's rewrite it, CH3 OH, hydroxide concentration, over the concentration of my conjugate base. So at the so when you find the concentration of acetate, you want to figure out the amount of moles. Well, it roughly be the same, right? So to find out the concentration of how we figure out 0.05 molar, you would do to figure out this concentration, you would do the milliliters of sodium hydroxide multiplied by the molarity of sodium hydroxide, and then divide that by the volume of 30 mils. So you do that by 30 mils, and you divide that, convert this to liters, right? This will give you, so convert this to, so the volume here, so milliliters should be in liters, but to figure out this concentration, you would, it might not be 0.05. So you need to use the, you need to use your volume of the equivalence point to determine this. So it'll be milliliters. So let's see. You're going to use the volume. So using initial, okay. So in this case, you want to use the, so to find this, so what we said was, let's just erase all this. So to determine this value here, we did, you want to consider the molarity of acetic acid and the volume of sodium hydroxide at the equivalence point. And then you want to also determine starting volume of acetic acid. Using all of these things, you can determine the. So using these, you can determine the concentration of acetate ion. And if all these considered, if you reacted all the moles of acetic acid in there with sodium hydroxide, then the concentration should be roughly the same. So roughly the same as the starting acetic acid. So that's why we did that there. So it should be the same. Okay, so use the molarity of acetic acid, the volume of sodium hydroxide at the equivalence point, whereas all the moles of acetic acid will now convert to moles of acetate, and you divide that by the original volume, you should get the same molarity, and that's how I got 0.05 molar. But now let's plug these numbers in. So acetic acid is, we will reform 3.2 times 10 to the negative third right here, and then it will be the same for hydroxide ion. Okay. And then at the end here, we get the molarity that we started with, 0.05 molar. Oh, sorry, not 0.05, right? We found the equilibrium concentration, and that was 0.0468. So that's a big difference there. Okay, so now let's calculate this value. We get 3.2 e to the negative third here. We're going to square that number and divide it by 0.0468. Okay, so we get a value of 2.1 times 10 to the negative 4, 2.2, sorry, to the negative 4. So that's our KB expression. All right, and so remember that Ka times KB is equal to KW. So we have a KB expression as well. Okay, so we go up here, we know that KW, KA then is equal to KW divided by KB. So we get, and remember, KW is 1.0 times 10 to the negative 14. And so we should get 1.0 times 10 to the negative 14 divided by 2.2 times 10 to the negative 4. So we should get, let's see here. 1e to the 14 negative divided by 2.2 e to the 4 negative. And we get a very large number. This is actually really puzzling. Let me see. A really small number, sorry. 3.2 e to the 3rd negative. We square that, divide by 0.0468. Oh, interesting. Okay, I might have done something wrong in these calculations. So let me just double check here. It might be because my pH was small. So maybe I didn't do exactly at the equivalence point. I might have done it at past the equivalence point. But so maybe my pH shouldn't be 11. So maybe my pH should be around 9. So let's change that up a bit. So let's make this maybe 9, because having 11 seems a little bit too much. So let's do like 9.25. Let's see what that value gives us. So we do that. So sorry guys, let's backtrack here. 9.25. Sorry about that. We get 4.75 for our POH. So then if we do the inverse log of that, so don't worry, your value should be much closer to the Ka of acetic acid, but so okay. Let's see. All right. And then we have now that should be a little bit larger or smaller. So we get 1.8. 1.8 times 10 to the negative 5th. Yeah. So 1.8 times 10 to the negative 5th now. Sorry, everyone. 10 to the negative 5th molar. And that will give us our concentrations now. So we get, so we're going to do something like this. 1.8 times 10 to the negative 5th. And then we have 1.8 times 10 to the negative 5th. And here is 1.8 as well. Okay. So if we do that, that should say 0.05 minus 1.8 e to the 5th negative. That should still give us pretty close to our value here. It's still roughly 0.04 9982. So that's still pretty close, 2.05. So now let's replace these values with the ones we calculated. So using pH 11, that's where it's pretty much hydroxide is going to take advantage of your pH. So that's why it was too high. So in this case, at the equivalence point, what matters is the only base present is the acetate and not hydroxide initially. So it'll have an equilibrium with forming the acid and hydroxide ion again. Okay, so let's do 1.8 times 10 to the negative fifth, 1.8 times 10 to the negative fifth. And then lastly, we have 0.049982. Okay, so let's try again. 1.8 e to the fifth negative squared divided by 0.0499982. So that gives us a value of 6.5 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that sounds a little bit better. 9 as our value. So now let's plug this back in here to 6.5 times 10 to the negative 9, and we should get a much closer value now. 1 e to the 14 negative divided by 6.5 e to the 9th negative. And we get something really close to 1.5 times 10 to the 1, 2, 3, 4, 5, 6. Negative 6 value here. All right, so that's our Ka. So it's not as close as we would have liked. So the Ka is actually 1 point. So the actual Ka, we actually determined this earlier. The actual Ka should be 1.8. 1.8 times 10 to the negative fifth. So we were close, but these values were made up. So what you would do is use your value, the actual pH. So you're going to use the actual pH at the equivalence point. So the pH at the equivalence point, you're going to use your actual pH here to determine your values. And if we just plug and chug, right? So maybe we try a pH of like maybe 9.8. So we do 9.8. Let's try that. We get 1.6 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we do 9.8. We get 14 minus 9.8. That gives us 4.2. And we do 4.2. Negative anti-log. That gives us 1, 2, 3, 4, 5. 6.3 times 10 to the negative 5. So we subtract that. So let's just do that right now. So maybe we have a different value. We have 6.5 times 6.3, sorry. So you see here, maybe my pH is off because I'm making it up. I'm making the data up. So 1, 2, 3, 4, 5. So it's 6.3 times 10 to the negative 5. And we would square that over 0.05 minus 6.5 e to the negative 5 e to the 5 negative. That still gives us 0.049935. And if we were to solve for that, the value should probably be closer. But just follow the techniques I showed you in these calculations, and you should be able to find your actual value. Okay, 0.049935, and we get a value of 7.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, -8 now. Now, this should be, I think, a little bit closer, but it might be too close. Okay, if we divide this now for our KB, KA equals 1 times 10 to the negative 14 over 7.9 times 10 to the negative 8. We will get e to the 14 negative divided by 7.9 e to the 8th negative, and we get, all right, this is much closer, 1.3. 1, 2, 3, 4, 5, 6. Actually, no, it's not. 1.3 times 10 to the negative 1, 2, 3, 4, 5, 6, 7. 1.3 times 10 to the negative 7. So this got much further. So the pH should probably be maybe not close to 10, but maybe a little like 8.5 or something like that. So let's just try 8.5 this time. Okay, one last time. So maybe our pH is 8.75. Who knows? So 8.75, we subtract that from 14. We get 5.25. Take the negative antilog of that, we get, so the POH is 5.25. And then our OH concentration is 5.6, 1, 2, 3, 4, 5, 5.6 now, times 10 to the negative 5.6, times 10 to the negative 5 molar. Okay, so 5.6 times 10 to the negative 5 molar. Now, if we do that constant, that sub again, we get 5.6 times 10 to the negative 5 squared over 0.05 minus 5.6 times 10 to the negative 5. And what is our answer there? 0.05 minus 5.6 e to the 5 negative. That's still 4.9944. So this is 0.04944. Okay, but what do we get for our value? 5.6 e to the 5, 5.6 e to the 5 negative squared divided by 0.04944. We get 6.3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 10 to the negative 8 as our KB. Now, if we divide that by 1.0 times 10 to the negative 14 divided by 6.3 times 10 to the negative 8 equals 1.0 e to the 14 negative divided by 6.3 e to the 8th negative. And we still get a value 1, 2, 3, 4, 5, 6, 1.6 times 10 to the negative 7. So still negative 7, 6. Okay. So we're still getting a value, but our value here was pretty close. When we had 10 to the negative 9. So when we had our Ka value of 9.25. So but am I doing something wrong here? I don't think so. So 10 to the 5.25 negative antilog. So I did get 10 to the negative 6. Oh, I think I did it wrong. 10 to the negative 6. Okay. Maybe I did do it wrong. Okay. Let's do 4.25 again. 4.75 negative antilog. Oh, okay. So I think it should have been 6. 5.6 e to the negative 6. squared divided by 0.04944 10. So this will give me a -10 value. So maybe I've just been dividing it a little bit too much. Okay. Then 1 to the 14th negative divided by 6.3 to the -10. Okay. Okay, that makes much more sense. So now you get a value of 1.6 times 1, 2, 3, 4, 5, -5 molar, or sorry, not molar, but this is your value. Okay, so it depends on where pH is. So my pH was just a little bit high. So your equilibrium or your equivalence point pH, use that value, and if you did it correctly, your value should approach 1.8 times 10 to the 1.8. Where's the actual? Sorry. Is it here? Did I have it? Let's see. I thought I had it. Huh. It was here a moment ago. Sorry, everyone. I'm losing it today. Right here. See, it's 1.8 times 10 to the -5. So it should approach close to that value. So see there, we can use that at the equivalence point, at the midpoint, and before the titrations, and we get we should get close to the values there, but please do it on your own, and hopefully this tutorial has been helpful. Sorry at the end where I kind of rambled there. Just so you can ignore that part, but I was just testing different pHs, and you see wherever your pH is, I think it should be before 11. Definitely probably near 8-ish towards 9. Because if I remember, that's pretty much where the equivalence point is, like 9.11, 8.7, stuff like that. So you should aim for that. But lastly, determine the concentration of acetic acid and acetate ion at the midpoint. So we already did that. So the concentration, so we kind of already just went over that right here at the midpoint. So the concentration of the acid is equal to the concentration of base, and that's because or that's the concentration where now half of your molecules of acetic acid got converted to half of your molecules at acetate. But we can show that. So the last part we'll do is determining concentration. So guys, this was probably long, so you don't have to watch all of it. Just watch through the parts that are more helpful to you. I apologize for rambling. Of acetic acid and acetate ion at the midpoint. So we know that at the midpoint, we have equal concentrations. We have concentrations of acetic acid equals the concentration of acetate. So what that means is that 1/2 of your acid molecules have reacted. So we write our ICE table here. Initial change, equilibrium, we have CH3, COOH plus sodium hydroxide. We'll go to acetate plus water. And here we have, so initially we have 0.05 molar, right? So we added 1/2 of that, that should be 0.025 molar. So we subtract this, 2.25 minus 0.025, we get, and this will give me X, and we don't worry about water. So in equilibrium here, we have 0.025, 0 sodium hydroxide, because at the equivalence point, we say we only add half of the sodium hydroxide to react with the acid. So all of the sodium hydroxide reacts. And that at this point, we have 0.025 molar. So the concentrations are equal. So at the midpoint, 1/2 your concentrations of your acid and your conjugate base should be the same. And we showed that right here. Okay. And by using that Henderson-Hasselbalch equation, or by just, calculating the pKa, which we did right here, we can determine the Ka of acetic acid. Okay. Determined. Okay. And then you determined the equilibrium. You can determine the concentration of H3O plus. That'll tell you the concentration of okay. So if we were to okay, let's see here. At the midpoint. So at the midpoint, it's competing, I would suppose. Dissociating equilibrium. Huh, interesting. So then you have it gets a little complicated because now the pH is now complicated by the fact that you now have two things going on. So now in this reaction, you have CH3, COOH competing with water to give you more acetate ion and water. But you also have this reaction going reverse. All right, but so one of them is going to compete. So these are competing reactions. Since your pH is probably still acidic, this one is probably the dominant one. So dominant reaction. And then to figure out the concentrations at the midpoint, you have this first reaction going on, but you establish more acetic acid still in solution and acetate. So you have to go a step further and so when this occurs, usually the concentration then will be determined by this reaction, where you find the pH. The pH here, I kind of wrote this incorrectly. H3O plus, and then here I have OH minus. But this is probably the dominant reaction. But I don't think you need to consider this. But maybe you do. So you record the pH. So at the equivalent, at the midpoint, right? So the midpoint pH will give you your H3O plus, and then you can figure out the concentrations of you can figure out the concentrations of. So use to find midpoint pH will give you, so the midpoint pH, you can find H3O plus concentration and then use this value to find concentration of acetic acid and the concentration of acetate. So let's just go over this one more time because this might be a little bit confusing. But you would essentially what I told you before, your pH, the amount of pH you found will be equal to, so for example, if your midpoint pH is, I don't know, let's just go up the same thing we did before. The midpoint pH is, so say our pH is 4.55, right? So pH is 4.55. Now we take the antilog of that. We would get, what did we do up here? 4.55. We did 2.8 times 10 to the negative second molar. 2.8 times 10 to the negative fifth molar. Okay. So we did our ice table, right? It's going to be, the dominant reaction is the acid reaction because the pH is still below 7. So CH3 COOH plus water gives us CH3 COO minus plus H3O plus. So initially we had, so at the midpoint we had 0.025 and 0.025 here. So initial change, equilibrium. So our change here, we're going to be 0.025 minus X, 0.025 plus X. So this is going to be, sorry, subtract X, subtract X. So our, sorry, plus X. So our 0.025 should give us some pH here at minus X, and here it's going to be 0.025 plus X. And the hydronium is 0 because we assume that there's no acid present anymore. It turned to water at the equivalence point, so it'll be plus X. Okay, so if we do that, we know that X is equal to 2.8 times 10 to the negative fifth. So if we solve for that, we will get and let's see here, 2.5, 2.5, 0.025 minus 2.8 e to the fifth negative, we get 0.024972. And if we do it right here, we adding our values here, plus 2.8 times 10 to the negative fifth. You see that it doesn't really matter because the numbers are so small still. Plus 2.8 e to the fifth negative, and that's still around 0.025028. And this value for X is 0.0 or still X. So this is going to be X, which equals 5 point, not 5, sorry, what am I saying? 2.8 times 10 to the negative fifth. Okay. So that will be our equilibrium concentration. So see how they're still pretty much the same. So if I were to calculate the Ka again, it will still roughly be the same, I think. So it'll be, well, actually, we don't need to calculate the Ka there. We already did that at the equivalence point. But if we were to calculate it again, we could do Ka equals my acetate ion, which is 0.025028 over 0.0024972. Oh, we also have to multiply this by 2.8 times 10 to the negative fifth. But you see here how these values are so close to each other, these values right here, that they pretty much equal to 1. But I guess when I spoke earlier, I kind of misspoke because we have to consider at the half equivalence, half the midpoint, we have to consider the contribution from the acetic acid reacting with the water. We can ignore the base reacting with water because it's so much weaker than the acid dissociation. So the stronger the acid, right, the weaker the conjugate base. So since acetic acid has a relatively lower, or bigger number or larger number than the Kb expression, because you remember the Kb we calculated, it was pretty small. So the Kb was like -10 in this case, or -9. So the predominant reaction will definitely be the acetic acid dissociating into the acetate. So if we do that calculation, you'll see right away that it's pretty much the same thing we kind of did before. 0.8, okay, 25.008 times 2.8 e to the fifth negative divided by 0.024972, and we still get 2.8 times 10 to the negative fifth. 1, 2, 3, 4, 5. Yeah, 10 to the negative fifth as my Ka. So it's pretty much the same thing we did. But you can just kind of equate these to 1 because they're close to 1, and it's 2.8 times 10 to the negative fifth. So so that's all the calculations that you probably had to go through. I went through all of them. Hopefully that was helpful. Sorry, just ran a little bit long, but if you just go through this presentation and you can do the post lab, and it should be much more simple. If students still have questions about these these ICE tables, please let me know and I'll be glad to help. But that's it for this tutorial. I know it's kind of a ramble. I apologize. But if there's any questions, please let me know. I'm always happy to help. Okay. So without further ado, we'll end things there. All right. Okay. All right. Okay, so let's see here. We could probably, oh, here's my video. All right. See you guys.